All right. So we did the introduction to group theory, and we had examples on the groups, examples of groups. We went as far as proving the theorem at 2.13. In a group G, there is only one identity element, and they managed to show that by assuming that if you have two, suppose we had two identity elements in there, then since the identity elements, they must be equal. So our supposition was we make them different and see how they relate. But the relationship turned out to be that they are equal. So today we look at another theorem that is just next to the one that we looked at. So today we're looking at theorem 2. So still looking at group theory. And let me try to increase the font. So group theory, and we're looking at some theorems. It's supposed to be looking at some theorem. So I meant this some theorem. Okay, I want it to be visible. This is theorem what? Theorem 2.14. That is saying, so I like the notes for 32 because you need to prove some things. And so if you're able to understand the proving, then it will be easy for us to solve the tutorial sheet to just be walk over it. So the theorem states that in a group G, the right and left cancellation laws hold. That is BA is equal to CA implies B is equal to C and AB is equal to AC implies B is equal to C. Okay. It looks too big again. How is the view? That's a Fine. Okay. So then you get the proof. So proof of this theorem. So you're saying in a group G, the right and left cancellation laws hold. That is, if I have BA is equal to CA, it implies that B is equal to C. The same as AB is equal to AC, we imply that B is equal to C. So now, to prove, we suppose one of them. So suppose BA is equal to CA. Then what will happen? Since we said every group has an identity element, so suppose that A prime is an inverse element of A. Then and multiply on the right. We'll say BA multiplied by A prime should be the same as CA multiplied by A prime. That is now right multiplication. So since multiplication is associative in such groups, remember in the group properties, multiplication there is associative. That is for G to be a group. So this implies that BA A prime is equal to CA A prime. I can do that if I want. I can put brackets, or I can't put brackets. It depends with me. So if I want to put brackets, I can put brackets here. I can put brackets here, or I don't put brackets. So if I put brackets, this implies that you know that this will just be B multiplied by the identity, because I've multiplied A with its inverse. And so the same thing happened to the right. Remember the properties of the identity, and that when it multiplies anything, you get that thing. So we have shown that the BA is equal to CA implies B is equal to A. And also, let me suppose again, let AB be equal to AC using the same inverse. We have that A inverse AB is equal to A inverse AC. This implies that by associativity again, A inverse AB is equal to A inverse AC. So again, I can get back and put the brackets here, put the brackets here, and get what? And get again, identity B is identity C. So nice, which implies B is equal to C. That is left and right cancellation. Very, very important. We need this somewhere. So I've picked it here, the theorem. We'll see how we use it in future. So what else? There's another theorem following this one, that for each element A in a group G, there's a unique element B in G, such that AB is equal to BA is equal to E. I mean, that one follows directly because you've seen that it's just a follow-up of this theorem that we had. Suppose that B is the inverse of A. Then we're going to have AB be the same as AA inverse. And you've seen that in this theorem, AA inverse is just an identity, which is what the theorem is talking about. So there will be no need of proving this one. Unless otherwise. Okay, this one we have no need. But we can prove the next. We can prove so we are saying, okay, so what have we said? We are saying that theorem 2.15, which says for each element A in G, there is a unique element B in G such that AB is equal to BA, which is equal to E. So we are saying the proof of this is just a follow-up of theorem 2.14. So I'm assuming that you've understood the follow-up I mean here, where you used this here, this guy. So you can see that in this part here is giving us what this theorem is talking about. That's why we are referring to it. Okay. So we're able to get that in that one. So let me move. Okay. Now I can go to 2.16. So 2.16 we need to prove theorem. So what does it say? It says for any group elements A and B, for any group elements, A and B, small letter A and B, we have that AB inverse. Now with my AB inverse is the same as B inverse A inverse. Remember, we use this actually in matrices, where you're saying if I'm multiplying A, B, and the inverse outside, I will switch them. We also use this in composite functions. So say G of F inverse will be F inverse of G inverse. So now in group theory, it's important that we get it, because whatever we've been using there came from this part. It came from group theory. So we need to have a proof, because now we are doing the actual thing that gives us what we've been using outside this course. So now, because of the left and right cancellation, it becomes easy for us to operate here. Okay. So we'll say the proof will suppose for the group, for the proof, you say, since we know that the left and right cancellation makes sense, then I can use it here. We get multiply AB by, so I get multiply AB by B inverse A inverse. But we know that this guy should be exactly the same as what? So if you multiply AB by B inverse A inverse, we said by associativity you can open these brackets. So it will be AB, B inverse, A inverse. Meaning, if we want, we can put some brackets here, like that. So the meaning of this is that we have A identity, A inverse. Because B multiplied by C inverse, we get the identity. And again, the identity here disappears. It will give us this, which also gives us the identity. Okay. If we switch, also B inverse, A inverse multiplied by AB is just B inverse, A inverse, A, B. Do this again, we'll get B inverse E, B, which gives us B inverse B, which is again E. This means that by definition of identity element, you remember we said, by the definition of an inverse element, remember that we said an inverse element, if I get A and call B an inverse element. In fact, it was this theorem here. Theorem 2.15. For each element A in G, there is a unique element B in G such that AB is equal to BA is equal to E. Then that unique element, in fact, we can add here to say, then B is equal to A inverse. So that's what we want to use here. So we're saying, since the exact element in that group G, that has the property that when I multiply it with A, I'll get the identity. Then I'll call that element an inverse of A. So if it's an inverse of A, then we know here that the inverse of AB should be multiplied by AB and give us identity. Now I have found an element here that is being multiplied by AB and it gives us the identity even if we alternate them. What does it mean? It means that AB inverse is equal to B inverse A inverse. The one we used in the doing of everything. So when we reach here, we say proved, not debate. So now we're laying the basics so that when we start looking at problems, it will be an easy thing because we know what we're talking about, because we have done the proofs of the theorems that are very important in those parts there. Okay. So now, if there are no questions, we can move. We look at some terminologies, some definitions. Some definitions. One, the order. The order. So we are saying the number of elements of a group G is called the order. It's called the order of G. Very, very important. Very important. Two, the order now. We also have the order of an element. The order of an element G in a group G is the smallest positive integer and integer n such that G power n is equal to E, the identity. So if a group G is an additive group, then you expect to get 0 when you do the NG, the idont square. And if it's multiplicative, you do the same thing. And you denote it denoted by order of G. That is an order of an element. Okay, this one is easy. We can have, in fact, you can have 2 examples now for these 2 definitions. Examples. Example 1, if you have Z4, you know Z4 is 0, 1, 2, 3. So you say the order, and you do not the order by this. So you say the order of Z4 is equal to 4. Any. So that's the order. Okay, so what could be the identity? What could be the order of what is the order of 1 in here? So to get the order of an element in this Z4, you ensure that you know how many times you're adding 1 to itself for you to get the identity which is 0, because this one, the identity here is, this one is an additive group. So the identity is 0 of this group. That's why there's no 4. Okay, 4 is being represented by the identity which is 0. So now, how many times do you get to add 1 to get 4? So you say 1 plus 1, you get 2. 2 plus 1, we get 3. And so 3 plus 1, we get 4, which is 0. How many times? How many times? 1, 2, 3. Remember, by definition, we are saying for this one, if it is an additive group, you say NG must give us E. It's like when I add here, I'll get confused. I know that if G is 1, then we are talking about N1 should give us E. So what will happen is N is 4. I think it's this that will give us 4, which is 0, which is E. My thought here is that the order of that element is going to be 4. I must be right. That's the order of 1. 1 plus 1. Yeah, right. 1, 2, 3, 4 is 4. Even here by counting, it's 1, 2, 3, 4. Yeah, so the order of 1 is 4. Good one. Okay, let's look at another example. This was for Z for additive. What if we bring in the multiplicative one? Multiplicative one. There's a long one here. Okay, let's try the same one. U10. U15, I mean. U15. And this one is multiplicative. So starting from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And multiplication, of course. Okay. So what we are looking, okay, so initially this is not the group I'm supposed to. The example I've picked is not like this. So reduce it to that form. The example is 1, 2, 3, 4, 7, 8, 11, 13, 14. Okay, so that we should not get used to seeing the last numbers there. 14. And the multiplication up to 15. Okay, so meaning that when you get 15, that's the identity. That's the meaning of the U15 there. Okay, so what's the order of the group? The order of the group, we count the elements in there. So the order of U15 is what we count. 1, 2, 3, 4, 5, 6, 7, 8, 9. Come on. Which one has 9? What are these? Let's talk about 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't need to understand this because the order, the number of elements in a group G is called the order of G. And so how many elements do we have here? Or I've put another element which is not in the group. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. The order of this is 9.
Sir, is 3 part of the group?
Why am I confused? Yes. 3 is part of the group.
But it has got a common factor with 15.
Yes.
Oh, okay, I get. Yeah, you're right. So it's got the, so meaning that it's the multiplicative thingy there. Okay, yeah. So it has gone back to?
It's supposed to be 8. 8, yeah.
Yeah, it's supposed to be 8 because of the 3 that goes in the 15. Okay, yeah, good. So it's 8. All right. So what happens now? So the order now, for the whole group, we have gotten the order. What else? Are we able to pick orders of independent elements here? So you can sample orders of elements. So now, yeah, you guys must be able to remember the modular thing. It also helps to get the order of elements. So sometimes you can get the order direct. Remember, when it is multiplicative, we are saying we want this. We want the Gn is equal to E. Okay, so let's pick what is here first. Suppose we get 7. We look for the order of 7. What do we know? We know that 7 power 1 is 7. And 7 power 2 is what? Uh-huh.
49.
49. Then how do we bring it back to the group?
We divide by 15.
How many times? So say 49 here.
So we have 4.
If we divide by 15.
Yes.
We divide by 15.
We have 3 remainder 4.
we'll have 3, that is 45, is it? 3 remainder,
Yes.
4. And then we get the remainder, is it?
Yes.
So this is equal to 4. So we're not yet there. So we extend, we get, let's get 7 power 3.
We have got 343.
343. We divide by 15. What do we get? 300 divided by 15 is what? Let's see. Okay. So I'm sure that, okay, let's see. 300 divided by 15. You can take 3 here. It goes 100 times. 3 here goes
It
5
goes
times.
22. Remainder 13.
So we'll have 20 here plus the 30, so 22. Remainder 13. So since it can't go in 13, then we are saying 7 power 3 is equal to 13, is it?
Yes.
Which is not the order. So we need to extend again. We look at 7 power 4. What is it?
2,401.
2,401. So we're cut, I think could be cut out of 10. So 2,401.